as you would expect because they're insulators. It's not quite that simple, but it takes a heck of a lot of hydrocarbon to drop the conductivity to the point where you can see it. So the devices are not useful, unfortunately, for a very large market, which is the detection of leaking hydrocarbons.
What did you actually see in that? You could see the tank from the
yeah.
prior survey. Is that? No, I mean the one before, the slide before that.
Yeah. What were we seeing?
What were you seeing?
Probably rebar in the tanks. Okay. But you can see concrete itself is quite conductive. Not by Australian standards, I might add, but by Ontario till. So you can usually see concrete as well. It never really cures, and there's still included moisture in it with some continuity. This is a survey site done with an EM34 down in Florida, and the line that you're going to see is line T2. And basically, the survey was carried out to see whether photolinears could actually be detected on the ground. It's typical layer cake Florida geology with not a lot of superficial material. And here are the traverses as you go down that survey line, traverse 2. And you can see the very classical anomalies that we discussed the other day, the sling ram type anomalies. And the giveaway for these anomalies is that as you go over a dike type conductor with a sling ram configuration, the width of these anomalies, which is roughly that, is equal to an intercoil spacing. So if you look at these ones here, they all look as if they're the same width. And the width turns out to be the 20 meters intercoil spacing used. So you can see that given reasonable conditions, they're sensitive detectors of structure. They're sensitive detectors of topography under the overburden too. I'll skip some of these. This is a kind of an interesting survey that was done in Lake Ontario. We're working here in Humber Bay. Here's the Humber River. Here's the shore, a man-made peninsula, Toronto that away. And here we have what is euphemistically called an STP, which is a sewage treatment plant. And here we have the outfall of the sewage treatment plant. The geology of the Humber Bay area is sand, nice, clean sand. And depth of water is about 20 feet, 6 meters or so. The trick here was to look for shallow conductive sediments in the sand itself. So looking in section, here we have the water, and here we have the sand. And what was done here was to tow an EM38 across the bottom on a sled. And of course the EM38 measures up as well as down. It thinks now that it's in a layered hole space. So what we did was to mount a conventional conductivity cell and a temperature probe on top of the sled that we pulled across the bottom of the bottom of the bay. The theory was that there's a fair amount of wave action here, and the theory was that the wave action would disperse the sediment from the STP outfall, which is a very fine material, and just shoot it out all over into the lake, and not seen is not there. The first slide shows the bottom temperature. All the measurements had to be corrected for temperature, and so there, as I mentioned, there was a thermometer on the device as well. And the temperature is what you'd expect. It's warmer in towards the shore, and the effluent from the Humber River is warmer again. It's also, I might add, fairly contaminated. This is the conductivity of the water. And what we did, of course, as I say, the 38 measures the total conductivity, but the conductivities are linearly independent of each other. And so if we know the conductivity of the water above, we can simply subtract it off the total reading to get the conductivity of the sediments. And so there's the conductivity of the water. A little bit of Humber River contaminant jacking up the conductivity at the mouth of the river, and a nice plume coming out of the STP. What you see, however, when you subtract that off and look at the conductivity of the sediments was a big surprise to one and all, without question, because the sediments are not drifting out to sea. They're staying right there, and these sediments have been there for quite a while. The other interesting point is that usually if we have this geology, the conductivity of the sand will be less than the conductivity of the water, typically by a factor of 3 or 4 because of Archie's law. In fact, in this case, the conductivity of the sand was about a factor of 5 more conductive than the water. It's really sticky sand. There's a lot in there. And I asked Gary Olhoff what he thought was enhancing the conductivity to that degree, and his answer was organic acids, which apparently are pretty conductive. This is a survey showing the use of the thing in a mobile mode. It's on the prairies out in Saskatchewan. Very, very flat. Looks like parts of Australia. We surveyed a half a square mile using the little tractor, and basically we kept on line by putting trucks at each end of the 1 mile section and just telling the tractor driver east or west, depending on where he was with respect to the headlights of the truck. And using that technique, this is not a particularly lovely presentation, but we developed the conductivity map that you see here. Basically, this is a mile by a half a mile. It's a half a section, which is a lot of prairie, I might add. And you can see that dryland salinity in the prairies is just about a problem as it is in Western Australia. These are the low background conductivities typical of prairie soil, 60 to 80 millisiemens per meter. And then in the conductive areas, the conductivities go up to 250 millisiemens per meter. There's a trick which the farmers use out in Saskatchewan and the southern Alberta when they want to sell their farms, which is they wait till the middle of January when they're covered with a couple of feet of snow and sell them to somebody from Toronto. That's a badly salinized farm. You know, in that area, the conductivities over about 140 millisiemens per meter are going to start to seriously impede crop growth. It's wheat country, and so over half of that area is significantly salinized. That's a comparison of an EM38 survey with a Wenner array. I've forgotten what the Wenner array spacing was. I think 1 meter, and you can see that in general there's pretty fair, you know, the conductivity variations are slowly varying compared with the length of the EM38, so you can see that they're quite comparable. And an EM31 and a 38, again, you can see a significant difference as a result of the 4-to-1 change in interquartile spacing. You can do another interesting trick with these devices, that the fact that the responses from all the layers add linear and independently is really useful. You can take the response curve, which I showed you here, for example, for an EM34 when used in this mode, and you can say, what would happen if I also used an EM31, which has a response curve that looks like that, the same response curve, but shrunk by a factor of 4. And you can say, well, if I take the EM31 data and multiply it by a factor, take the 34 data, multiply it by another factor, that basically I can alter this response curve to almost anything that I want. And in essence, you can use it to strip off the near surface material. We often talk in EM and resistivity of wanting to strip off the near surface contribution. Well, these instruments are the one where it really works because the sensitivity or the response from each layer is independent from all the others. So you can design whatever response curve you want by varying with the fudge factors that you multiply the data by. And in this case, this is an EM31 survey in an area where we're looking for gravel. So in this case, gravel aggregates tend to be low conductivity, so we're looking for the blues. And you can see that we have some low conductivity areas. Most of the area is pretty conductive. This survey shows an EM34 survey over the same area. You'll see the blue area up here is showing up, but most of the near surface material was conductive. Once we get the larger spacing EM34, the near surface is less conductive. And the third slide shows the results of multiplying the data so as to give us a response curve which is very low to the near surface material. And here, in essence, we have stripped off the near surface material. And the results are that these anomalies are actually quite a lot bigger than they looked on either set of data alone. You can use them, obviously, for monitoring salinity with time. In Canada, out in the prairies, we have a number of potash mines. And they take the waste rock from the potash and they mine and they just dump it on the surface. Has anybody seen one of the potash mine disposal sites? The tailings pile is about 30 meters high, and it can easily be a square mile or more in lateral extent. These are big piles of salt. And of course, the salt in them leaches out and into the surrounding prairie. Here's the potash site. And there's a series of profiles done across the face as a function of time, 1982. So here's distance away from the face. Here's the conductivity. You can see the front moving out with time and eventually saturating after a few years. They're used for tailings ponds as well. This is a mine in northern Canada. And it simply shows surveys done with EM31 and 34s at different spacings. And you see a very, very sudden change of contamination with depth. And another one. I have a lot of case histories. Well, okay, yeah, that's good. What Alex brought up the point that you can also use EM very effectively for induction logging. What you do on the surface, you can do equally well in a borehole. And as you pointed out, the induction logging market has been going for years and years and years and years, and is relatively, well, Alex, I guess, is very sophisticated. What you see, or we'll see here, is a very simple induction logger. Again, it's designed for environmental applications, so it consists of two coils 50 centimeters apart. And in fact, there's a third coil in between the transmitter and the receiver. And what that third coil does is help to get rid of the influence of the water in the monitoring well, the conductivity of which is usually fairly high. What we want to do with these devices, of course, is not measure the conductivity of the water in the well. That's easy. We want to measure the conductivity out in the surrounding soil. And basically what they're used for, if you have a contaminant site, you put in a monitoring well. Usually in North America they're 4 inches in diameter, and they're PVC cased. And what you do is you put down an induction log, You want to tell where the contaminant plume is vertically, because you want to sample it. And what you do is you have sections of your casing that are screened. And you put, obviously, the screening in the areas which are contaminated, and then you can, over time, pull up water out of the well and sample the degree of contamination. What they're very worried about in the U.S. is inter-aquifer contamination. So you have to be very careful where you put your screening. If you make the screening too big, and you have, for example, a contaminated aquifer down here, an aquitard, and an uncontaminated aquifer above, you can get aquifer contamination as a result of transport of the contaminant from one aquifer to another. So the placement of the screens is always a problem. How the hell do you tell when you've drilled a borehole where to put the screen? And there have been some mistakes made. This device is very, very short. The coils, as I say, are 50 centimeters apart. The radial response looks like this. It's maximum about 30 centimeters away from the borehole axis. The response on and near the axis is very small. And the vertical response looks a bit strange because of the presence of the focusing coil in the center of the probe. And the net result is that the equivalent of this curve for these devices looks like this in the borehole itself. So that would be the response of a thin layer as we move the probe progressively by it. This is a comparison of the induction log with a 16-inch normal log. And in general, you'll see that there's good agreement between the two. Areas where there are poor agreement are areas, for example, where you have thin resistive beds. The induction log will have great difficulty seeing them. And so, for example, areas, that's going to be, I'm not sure which way those go. It's hard to see from here. But anyway, when you go over thin resistive beds, they look different, and also true for thin conductive beds, which the induction log loves to see. But generally, you can see that there's good agreement between the two in the open hole, and then this shows two measurements done with the induction log in a cased hole and in the uncased hole. And again, apart from a bit of instrument drift, you can see that the conductivities are the same. One of our users, who was quite a skeptic, decided to check our mathematics and our engineering, and he took his 39 out and he dropped it into a conductive lake in the USA. And that's a comparison of the measured and theoretical response as you drop it into a conductor. In that same area, I have here the response. This is hard to see, but this is conductivity out to about 2,500 millisiemens per meter. This is depth again, 10, 20 meters. And I show here two logs. The first is from a gamma ray, a simple gamma ray scintillometer, the output of which is roughly proportional to clay content. And I also show, that's great, thanks. I show an induction log sitting on top of it. You'll see two responses from the induction log, a huge one near surface and a much smaller one down about 15 meters. The one at near surface is uncorrelated with the gamma ray log. The one down deeper is well correlated with an increased gamma ray count. So this small increase in conductivity is probably to be attributed to increased clay content. This big plume up here, this big high, is obviously from leaking brine out of the tailings pond. This is another survey down a borehole where the borehole is next to a landfill site. The near surface water, near surface soil is uncontaminated. Once you get down beneath the water table, the conductivity starts to climb, and the contamination increases with depth. More interesting, in an adjacent monitoring well, the probe shows fingered structure in the contaminant plume. And the interesting aspect is that if you look at enough induction logs, you start to realize that even in sandy materials, that it takes an incredible small amount of clay to keep a plume up out of the next aquitard. And usually it's small enough amount of clay so that it will never be seen in the driller's log. So using these devices, you can detect this fingering. Obviously, it's important to decide where you're going to put the screen in a plume of this sort. And you note here the really very sharp boundaries of the plume. It's obviously being held up here by something, and likewise there. This is a modeled response for that plume. It's easy to calculate at low induction numbers the response from a layered earth. And this is the geoelectric model sitting on top of the measured response. And you can see where, in many cases, the boundaries which the model gives agree with lithological boundaries picked up by the driller's log, but in other cases, definitely no. So they do have application for this. And the last case history is done again. We love landfill sites. This was in New York State, and there are two, this is in the city of Albany landfill site. There are two holes out here, a shallow and a deep monitoring well. There are many more. There are monitoring wells obviously located all around the landfill site. And these things are logged regularly to decide whether the leachate from the site is getting off the site. And these are the lithologies from the two monitoring wells. The long one shows virtually sand, some silt, some clay, but in general sand until at the bottom they hit a gray clay. So naturally that's where they put the screen for their monitoring well, because that appears to be the aquitard. The short well shows basically just sand, and they just put the screen at the bottom of the hole because they couldn't think probably of anywhere else to put it. And so we ran the induction log down this hole. And there's the result. Most of these holes are steel cased at the top for half a meter, a meter. So what you see here is no response, and then the device kicking as it comes out of the casing. Here's the shallow well with its screen indicated, and here's the deep well with its screen indicated. And what you see is a huge great plume in between the two wells. And they were totally ignorant of the fact that the landfill site was leaking out in this direction. As we pulled the probe out, one of the guys asked us whether we were worried about touching the probe after we pulled it out of the hole, and we said no, we weren't worried at all. They'd obviously missed the contamination with their screens, and we were sure the water was just fine in the well. Again, it's possible to model to fairly high accuracy a layered earth that will usually match the measured profile. One reason for doing this is to see what sort of resolution we actually do have for a vertical interface. And what I show here is the measured response here, the calculated response there, and I vary the nature of this transition. And as I do it, I start here. You remember I had an abrupt transition here. I relax that and I say, okay, I've got a transition of total width 1.3 meters. In other words, I postulate that geoelectric section, and I see that there's a large amount of divergence between the measured and calculated response. As I narrow this down, and my objective is to see how narrow I can make it before these differences disappear, I see that once I have the transition of width about half a meter, 40 centimeters, that it's not possible to improve it. So basically, that's the sort of resolution that you have in the vertical direction. Okay, I think that that's probably about it for case histories. As I say, they're simple tools. They're designed for geologists, and that's not meant to be a snide remark, because we like to say that if we give one of these things to an engineer, he goes out and he does the survey, and he said, I got 68 millisiemens per meter over there. What does that mean? And of course, the answer is nothing. If we give it to a geologist, and then contours out the data, the geologist usually has a pretty fair idea of what the geology is, and he basically simply looks for geological or morphological features in the contours to see if they agree with his understanding of the underlying geology. Good. Are there any questions? Simple tools, simple use of EM, but a very popular one, and within its limits, pretty effective devices. Yeah.
When you run the conductivity tools for magnetically susceptible material, you get a series of effect. Basically, you can no longer separate conductivity effects from
At the low induction number that these devices are working for, it turns out that the in-phase response is responding apart from metal in the hole. And everybody will swear blind there's no metal in the holes. There always is. There are drill cuttings and that sort of thing. But the in-phase response responds to susceptibility. And so I didn't show any slides here, but we actually use the in-phase response as well to map susceptibility. And it turns out to be really interesting. It's a useful logging tool. It's of course useful to people who are in hard rock mining, but it's also useful to the hydrologists, particularly in Canada, where you'll often get mafic pebbles in layers and that sort of thing in the glacial deposits, and these things stick out with a bang, and they may or may not show up in the conductivity. So susceptibility, even at these low levels, and we're measuring susceptibility at 50 to 100 part per million levels and less, is quite a useful tool.
We've been running conductivity bolts, not a geologist,
Yeah.
through sections of laterite here, which are sections which are highly susceptible.
Yeah, you'll certainly see that.
They separate.
Yeah. No, you'll notice that I'm talking about much lower levels. One problem with these devices is that if you're measuring the in-phase signal and the ground starts to get very conductive, you'll also get some in-phase signal arising from the conductivity. So sorting them. The quadrature stays, Alex, it stays, eventually it saturates out. That's correct.
It seems to me like you can't separate them.
You cannot.
Yeah, Graham, it depends on the values. Yeah. One other problem is sticky susceptibility. If you have, we were discussing at lunch today or earlier, the susceptibility, finite dielectric, finite relaxation losses in the susceptibility, and of course if you have those, they will come over and give you a quadrature phase component from the susceptibility as well. I don't think we've ever really seen it. These things operate at really low values of induction number, I might add. They stay linear out to about 10 Siemens per meter. Now, that's nothing compared to massive sulfide, but it's a pretty contaminated site. Okay. Good. Alex, going to get home early. Yep, unless you have some more. I bet you that's not going to be too unpopular. Okay.
Okay, so that's it for today.
Yeah, I think that's. So we can discuss next topic. Now I will discuss with you skin effect, what I started before, and diffusion, the most essential phenomenon of all electromagnetic matter. At the beginning from physical point of view, then a little from mathematical point of view. Very little, only to give idea what are the equations which we use. Now, first of all, I remind you our subject of last lecture yesterday. That's conductor. Uniform, not uniform, doesn't matter. As soon as source, for example, current loop is located above, and as soon as function current in transmitter changes as step function, not sinusoid, step function, then at the first moment when we turn off, no current inside, no. Point number one. Currents appear only on the surface mainly on that part of the surface which close to transmitter, relatively close to transmitter. What else? And magnetic field inside remains the same as before at each point. That's the skin effect. And nothing else. Only this picture has named the skin effect, which is a very important part of our understanding. Now, again, it could be water, it could be rock, it could be beautiful metal. Effect is the same. For instance, now if I take glass of water, here I put transmitter, shut off almost instantly current, I claim on the not on the surface of the glass. Glass let us consider insulator, but water is conductor, and therefore induced currents arise on the surface, not on the internal, where the water between glass and water, and they are distributed in such clever way that field remains at the first moment is constant. That's skin effect. Now, suppose I have shell conductor, air, and air. Case number one, that's conductor. Again, doesn't matter what is it, water, metal, water, clay, sand. If you have transmitter here, doesn't matter how it's oriented, matters is step function. That matters. If you turn off current, where current arises? At here our conductor confined by two surfaces, S1, S2, correct? Here air, here air. If transmitter is located here, currents arise only on the external surface. Again, on the surface which is closer to transmitter, close. Now, second scenario, transmitter I put inside, again, free space. Please don't consider literally this size. It could be very small, it could be very large. I turn off transmitter, currents were arise at internal surface here. In such way, they do create the same field where inside of conductor. Now, is it clear picture? Very clear? Good. That's the skin effect with which we deal very, very often. It does not have any relation to skin depth. It's phenomenon. It's as electrostatic induction, as electromagnetic induction, as polarization. That's one of the most important phenomena with which we deal throughout electromagnetic activity. Now, one small question. Just a second. Where is it? Perhaps there, yes. Our conductor, our transmitter, has behavior of the current. We know at the first moment T equals 0, currents arise on the surface in such way that field inside at the first moment equal primary field. Correct? I don't tell anything new. I simply repeat what I told yesterday and then end. So the role of this, the function, role of this induced current is only one: to create magnetic field which was before. Therefore, at the first moment, this current is independent on what? Conductivity. They don't depend anything except not geometry and primary field, because their goal is only one: to create inside such field which was before. Do I speak clearly? Now, therefore, whether it's metal, whether it's clay, whether it's sand, whether it's water, intensity of currents at the first moment is the same. It's completely independent on conductivity. Now, what about outside? Since there are currents, surface currents, then they create magnetic field. So if you have receiver which measures at the first moment magnetic field, you can be confident you will have magnetic field at the first moment, which is no common feature with primary field. Primary field remains the same where? Inside. But I didn't mention that it must be the same outside. Outside will be field which depends on geometry or where you measure, but it's independent on conductivity. Now, so behavior of the field at the first moment when we use step function is the skin effect. For us, it's important to understand that currents arise only on the surface. If 1,000 surface, choose surface which between transmitter and receiver. And moreover, usually maximum intensity currents at that part of external surface which is close to transmitter. Of course, outside there is new magnetic field which reflects geometry of conductor, its position, but no means conductivity. So that's the reason, I think I emphasized a couple times already, that's the reason that early stage is not proper stage. Now, suppose it's ideal conductor. What happens with this current? It will move without stopping, without changing, We created current. Current, it means amount of charges, movement of charges. Current density, amount of charges. So this amount of charges will be the same all time if it's ideal conductor. Because ions or electrons don't meet any resistance. But what happens next? So skin effect, I hope we do understand. What happens next? Next moment we start to observe in general case when conductor is not ideal, that's general case, normal case, natural case, we start to observe diffusion, completely different phenomenon which does not have any relation to skin effect. It tells you what happens a little later after skin effect. And then we will consider examples for our models, skin effect, diffusion. Now, general picture. Before I start to tell about it, let me return to my lovely ring. We had current ring, transmitter, and we found out in single current ring, not solid body, in single current ring, induced current is equal primary flux divided inductance T over tau, where tau time constant of the ring. Tau equal A over R, correct? So, did we observe here similar phenomenon? Yes, we did. For instance, at moment t equals 0, what we found out? Current arising in the ring is independent on conductivity. Because only tau depends on conductivity, correct? It's defined by what? One requirement at the first moment. One requirement. Current must be such that current times inductance must give primary flux. So complete knowledge. So everything what I'm telling you can check practically using simple examples. Now, then it's not too bad to look what happens here. Here, in effect, we observe the simplest case of diffusion. I would say one side, one feature of diffusion. What is the feature? Current charges are moving, meet resistance, and electromagnetic energy transforms into heat. And that's what this term shows. So always we have to observe transformation and decrease, no exception. Now, but here it's interesting, simple expression, but it tells us something very, very interesting, useful. If you can forget about sharp step function, let us ask ourselves how long we will see this skin effect. Do we see this skin effect only at the first moment or a little later? And we know how to answer this question. Suppose tau is large. Tau equals 100 milliseconds. Please imagine you are dealing with conductor which has time constant 100 milliseconds. How long we practically observe skin effect? Theoretically, we observe at first moment, t equals 0. True? But let us ask ourselves, we are engineers, we are applied area students, etc. So how long practically we observe the same behavior, not only at the first moment but a little later? Everything is defined by time constant. For instance, if I take t equals 10 milliseconds after turn off, 10 divided by 100, it will be exponent in power 0.1. Is it correct? 10 divided by 100, 0.1. So, is it close to 1, or it's a very close? It's around 0.9. So, what this skin effect as phenomenon, where currents are distributed on the surface, practically manifests itself not only at the first moment, but a little later. How later? It depends on time constant. The greater time constant, more conductive body, slow transformation into heat, and it will be later. If you have very good resistor, completely different story, you still will observe time skin effect, but only during very short time. So after defining skin effect, I would like to make it more practical, so it absorbs not only the first moment, but also during some interval, which depends on time constant. Time constant is extremely important parameter which tells you what is going on. Now, back to this example. In this example, we also observe diffusion, but in a very restricted sense. We only observe two features. First of all, at the first moment, current is such that it creates the same flux. And second, we observe decaying of the current at the same place, one ring, with time. But we don't observe the third very important feature of diffusion. Why, in effect, it's called diffusion. Let us do observe it. In order to observe, we have to look into conductor. So far, understandable? Good. So, at the first moment, we have induced currents on the surface. If there are induced, if they remain, let us consider case of an ideal conductor. No more current in transmitter. Agree? We turn off. Please completely forget about transmitter. It did its job. It created surface current, and then let us forget, it doesn't work more. So, what we have? Only surface current. If we deal with ideal conductor, tell me please, what happens with magnetic field inside of conductor if it's ideal? Huh? Sorry? Stay the same. Current remains the same. Constant current remains the same. The same, different at different points, but the same as function of time. Or not? So if it's ideal conductor, current arose on the surface, no transformation into heat. So intensity of current, for example, we had 1 milliampere per meter square. It remains the same. Understandable? There is only one reason for current to change, only one. If there is transformation into heat. So, current remains the same. Therefore, magnetic field at each point remains the same. What is the value of the magnetic field at this point? It's a question for learning, for checking your learning. The same as primary field. The same. So it remains the same. It remains the same. It does not change with time. Therefore, question arises. Do we have here electrical field or we don't have? So that's a very important question. So I do consider ideal conductor. Clearly, current remains the same. Magnetic field, therefore, according to Biot-Savart law, remains the same at each point. It's different points, but does not change with time. Therefore, now my again question. If magnetic field remains the same, do we have electrical field inside or we don't have? Why we don't have? I am very happy with the answer. Now I will be much more happy if you explain me why no. Huh? Sorry?
We're changing magnetic field.
So when you are saying, you rely on which physical law? Huh? Faraday law. Faraday law tells no way to have electrical field if flux does not change or magnetic field does not change time. Now, there is another generator of electrical field, but we don't have it here. Charges. So, we don't have charges, we don't have change of magnetic field with time. Engineers, we must say, no electrical field. No electrical field, then no inside. A lot of electrons inside of conductors, a lot of ions inside of salt water, but they will not move in a regular way. They will move randomly. But that's not current. It's a noise for current, it's very small. But we will not have current. Why? Because no force. So according to Ohm's law, if we don't have electrical field, we don't have current. So at the first moment of skin effect, we have only surface current here. We do have magnetic field inside, and we don't have electrical field, and therefore inside. Understandable? That's the picture of skin effect. Now, back to reality. After first moment, when we do have skin effect, when surface currents arise, now we would like to see what would happen. Ions or electrons are moving. They need resistance of the medium, near surface. That skin, it means surface. That's how it's called. So let us describe, must be complete justification of this name. That takes place. Now, ions are moving, hit walls of pores each other, therefore friction is working and part of energy transforms into heat. Very well. Therefore, what happens with density of current at this point? It starts to decrease. Aha. Current decreases with time. Therefore, what would decrease also? Magnetic field caused by this current. Now, if I take any point here, I cannot say more that electrical field is zero. True? Aha. Due to friction, and therefore transformation electromagnetic energy into heat, surface current changes with time, therefore its magnetic field changes with time, and therefore electrical field arises inside of conductor. It's very clear. If it's a good conductor, very good conductor, then rate of change is very small. Therefore, electrical field small, so induced currents are not in hurry to arise inside. If it's a resistive conductor, resistive body, then surface currents decay very quickly, therefore strong electrical field arises and currents more quickly arise inside. This phenomenon of appearance and behavior of currents inside of conductors after first moment, after skin effect, is called diffusion. And that's what we are dealing in all electromagnetic methods except radar, where, by the way, diffusion, unfortunately for radar, plays very important role. But pure diffusion we observe in all methods, such as time domain, frequency, control source MT, magnetotelluric, VLF. All methods, without any exceptions, are based on diffusion. Now, let us investigate this phenomenon, if you don't have questions. How to attack this problem? Let me do the same way as I did in case of propagation. Maxwell equation, let us not forget about, this is the basis. Maxwell equation, we replaced one equation, which I call D'Alembert equation. D'Alembert. Let me write. And then again we will return back to physics. Equal gamma mu dB dt magnetic field minus epsilon mu dB dt squared equals 0. That field, that equation, which is exactly equivalent Maxwell equation, which describes at any point behavior of magnetic and electrical field. We have only replaced B by E. Now, when I consider with you propagation, I neglected by this term. I consider in an insulator. Now let me do opposite. Let me neglect by propagation, because we made some evaluations and found out for our separations between transmitter and receiver, every propagation takes place before we measure. So let us not, it does not exist. Simply we measure after this phenomenon take place. So we neglect by this term propagation, and we got equation which once I mentioned gamma mu dB dt. This equation is diffusion or heat equation. It's used in physics widely. Physics and chemistry, when it describes motion of ions, it's diffusion, it's a propagation, diffusion of heat, and finally it's equation which is basis of all phenomena, all our studies. So I do advise you at least to know this equation. What is the difference between wave and heat equation? From pure formal point of view. Heat derivatives in both cases with respect to coordinates, but in the case of wave phenomenon, here there is a term where second derivative with respect to time. In heat equation, always first derivative. That's all. Pure formal. Now, approach. Now, let us consider one model. The simplest model for which we will find solution. Not find, but I will write down. Let us assume we have uniform half space. Uniform half space. We always start from uniform half space everywhere. With resistivity gamma, magnetic permeability, zero. Let us imagine unrealistical case, very unrealistical, extremely superficial. Let us imagine that's our axis Z, that's axis X, and we have huge metal plate, foil. Again, that's air, that's conductor, and let us assume amazingly powerful transmitter. Everywhere currents in metal plate go along axis X, uniform plate. So we created. How to create it? In practice, there is one good method which does not have any relation to our subject, an electrical method in old time, 20s, 30s, when we try to find electrical, we try to find deposits, good conductors. Sometimes we used many electrodes, A, and that's B, around kilometers, that's surface, that's conductor. So it's in this case, it's a grandfather of control source MT, but children became much worse than parents. And that and this 20s, that's plus, that's minus. A current really travel in this direction. Line is very long, many electrodes, 500 meters, kilometer distance. Even it's called method of equipotential lines. And somewhere in the middle, it was voltmeter. Since not in 1/3 of the in the interval, which around 1/3 of the distance, electrical field everywhere uniform, primary electrical field. So it's a nice situation because the simply primary field, they easy, in principle, it's easy to detect conductor or high resistive target. So it's possible to create this uniform field from completely different areas. Let us assume we have here electrodes and created constant current. For us, it's important that current here does constant. It does not change in perpendicular direction along axis S, X, along axis Y. Now, let us assume that at some moment this current was stopped, step function. Let us describe what would happen. This is the simplest case, not practical, but simplest, which illustrates physical idea, nothing else. Can you help me after our conversation? What would happen? Earth surface, uniform medium, even non-uniform, but we are interested by uniform medium, and here plate where current, primary transmitter current was stopped at moment 0. What happens at the first moment? Currents will arise here. They will still move in the same direction in order to create old magnetic field which was before. True? So nothing would change, only instead of transmitter plate, currents will arise on the Earth's surface. Then we have to describe what happens next. Let us look in our heat equation. We have only one component of current, Jx. Current depends only one coordinate z. Why? Because we don't have Jy, Jz current density. Field is independent. Therefore, this complicated Laplacian from current density, electrical field current density, simply becomes dgx dz square. Because if you remember, Laplacian sum of second derivative. Now, therefore, all our heat equation becomes equal gamma mu dgx dt. That's the reason why I took such unrealistical case, as I did, by the way, in case of propagation. So we have only one component of the current. So this Laplacian is simply derivative with respect to z, no derivative with respect to x, no derivative with respect to y. That's a very simple equation, which is very often used in textbooks. Now, let us ask ourselves, does this equation describe skin effect? No, because skin effect is everything what happens at the first moment. Now, this equation tells us what happens later. Since it's a very simple equation, very simple, relatively simple, let us say, its solution has very simple form in our case. Let me show you. In our case, it has the following form. Jx as a function of t and z, it depends on time, and depth is equal some constant, let us not write constant, unit divide time, square root of time, e minus t, some constant a divided by t, where constant a is equal gamma mu z square over 4 elementary functions. That's the reason why I chosen for you this example. Some constant c, that doesn't matter. So again, at each point, current density equals some constant, don't pay attention, time, and again time, and parameter A is independent of time. It's equal gamma mu, point where we study, divided by 4. But if you would like to play game with this formula, it's very convenient. So it tells us secret about diffusion. Let us discuss it. Let us start. We will start a couple of minutes and then we'll stop. So again, since we touched a little mathematics, let me remind chain of events, physical law, Maxwell equation. Instead of Maxwell equation, heat equation. That's solution for simple case. Now, if I ask you, since it's simple, let me ask you. Point Z, any point Z. Tell me please, what would be behavior of current at any point Z as a function of time? Z I fixed. Look please in this expression, nothing else. Small exercises in back and forth. I took depth 50 meters, Z equals 50 meters. My question is, first of all, do we know what is the value of current at the first moment when current turn off? What is the value? Nothing, 0. So let us check, does this formula tell us it or no, or it doesn't? So what is the conclusion? Huh? So I hope during break you will not rest and continue. So solution of this diffusion equation is the simplest case which is possible to imagine. The simplest. No way to find simply. That's the reason why I brought your attention. Solution has this form. Now, let us read this result. Again, at moment t equals 0, we have skin effect. It does not have any relation to diffusion. We solve this problem. We not solve, I explain. Now, in order to understand what happens with current later, we will use this simple equation. But I found out we have small problem. Now, let us find out. So I fixed point Z. Now, let me ask you a couple questions. It's useful. I know it's useful regardless of electromagnetics. If I have function y equal x e minus x, and x goes to infinity, what happens with this function? Huh? It goes to Why?
Because the e goes very low.
X goes to infinity. Yes? This part is correct. Now let us look in this function. What is happens with this function when x goes to infinity? Huh? So there is a fighting. Simply fighting in opposite directions. One goes very quickly. One goes to infinity, another goes to 0. Yes? True? Which is who is winner? Huh? Sorry? Exponential, of course. Exponential, nobody can compete with exponential. That's why when we say exponential behavior, either it grows extremely up or it decrease extremely quickly. So limit is how in calculus it's called rule when you would like to resolve this? Huh? Yes, elliptical rule. So exactly the same story here. Make replacement x unit divide t, you will get the same result. So when time goes to 0, I understand your concern. This function goes up. But this function decreases. So everything is okay. At the first moment, you don't have current here. Clear? Then, what happens when time is very large? What happens with this term? It tends to 0. What happens with this term? If time increases, it tends to when time increases, power tends to 0. Exponent in 0, power 0, 1. So it will decrease. Now let me plot you graphs. And then you will see in the simplest way diffusion. There are some features which will be incorrect, but I will show you case when everything is correct, very important, but it's only for illustration, diffusion. Now, if if z equals 0, that's except time equals 0, it's this term 1, so this term will give you current on the surface, correct? So, let me plot the graph T, gamma nu, I hear current at each point, at each moment. Divide by current at the same moment on the surface. In effect, I know x. And graph will have the following form. That's for z equal z1. Any z, any distance, 1 meter, 50 meters, doesn't matter. Let us fix. Now, I use this expression, nothing else. Where is the z? In this coefficient. So I fixed the depth. We started to watch what happens with time. That's what happens with time. Let us read what is written here. At the first moment, t equals 0, no current, skin effect, you see? Then current begins to increase, reaches maximum. It's not too bad in mining prospecting, measure when primary field is large, near ore body. Then it reaches maximum and then goes down, decays. So what I am doing, I observer who measures current, the same behavior, magnetic field, etc. I watch what happens with density of current at any depth. I would like to create field. I would like to create current. That is the same behavior electrical field according to Ohm's law. Because if you remember, current equal gamma E. So gamma constant. So it's behavior electrical field also. Now, so if there is a range of time, when you don't have field at all. Then time increases, and signal field increases, reaches maximum. Then what happens? Since you found out from here, I understand from physical point of view, it's clear that energy transforms into heat and current starts to decrease. Now I would like to compare behavior of current at the same time, at different depths. Just a second. Oh, that's not very clear picture. Now, so suppose it's a Z equals Z1. Let me take close. What would happen if I start to study behavior of the current close? Can you help me to find out what would happen?
You reach the maximum faster?
Faster, exactly. So you will have what? Z0. Then, if I would like to look deeper, behavior graph will be Z2, Z3, and etc. So all the in general features will behave in the same manner, but there are very essential differences. At the closer you to the surface, the early current appears, and it's rather strong. Then it decreases. With increasing distance, you still have the same feature. However, there is a difference. What is the difference? Maximum of field appears later. Second, width of the pulse becomes bigger. Diffusion. The greater distance, the smaller maximum, and wider, and later. That always takes place. No exception at all, regardless how complicated model. So we don't derive anything, but it's not too bad. I'm trying to describe you main features of quasi-stationary field. So you will not make mistake if you say, if I created by source loop step function excitation, I observe always the following. On the first moment, on the surface current arises. Surface current, which does not contain any information about conductivity, electrical conductivity. Then, with time, at each point, I will observe several features. At the first moment, unlike surface, no current at all. Then density current will increase. Then it reaches maximum. Then it goes down. The deeper I am located from the surface, the later I will observe this maximum. And amplitude of maximum always will be smaller with increase of distance. Width of the maximum will be great large. Now, what else? That's the principal difference between else is the following. Sometimes, during 17 years in the United States, along with consulting many good companies, sometimes I was invited, since I was not related with established groups of geophysicists who had constant contact with industry, I was invited sometimes companies which perform special type of cells. For instance, in Calgary, there was a company called Electroflex, which was very successful and end of 17th and beginning of 80s, small company. And they invited me, they expected that I will help them to explain what they are doing.
I was not able to explain. But what they did, they put loop or grounded line, more precisely, on the Earth's surface and created step functions. And they claimed the impulse step function, which describes behavior of the current, will also describe behavior of the field. Therefore, when this pulse travels into ground, when it hits collector, understandable what collector means, with oil or gas, then it reflects back without change of shape, without anything. So it's how they thought. They thought in the following way: radar is excellent device. It was excellent device, best device, especially Second War, to detect planes. You send pulse, without change, it hits, it travels, propagates through medium, hits plane and reflects. And shape remains the same. Why it happens? Because fortunately air is practically non-conductive. They thought the same is true for conducting medium. No common features at all, unfortunately. And finally company went down. But not because of the pressure, because physical ground was completely different. It's called in United States, I don't know how it's here, but in North America it's called black box company. Then in 80, but it's so attractive idea, especially for people who don't understand. One physicist from Syracuse University in 84 invented another box. He told at the frequency 28.6 kilohertz, seawater becomes non-conducting. Not low, not high. And he was physicist. He made box, and he claimed that at this frequency energy goes without attenuation again to the collector beneath ocean, Atlantic Ocean, and if there is a reservoir, it will measure effect. So, of course, there are many people who, investors, who don't have any relation to physics. It was so attractive. Even there were several flights with this box. Even a lot of money was put into company. And it happened in such a way that I had to review this proposal. So what I would like to say, that's what really we have. No relations with radar, impulses, propagation. For good or for worse, we are working with diffusion with all its advantages and disadvantages. Of course, it would be very desirable to create impulse in our wires, and without attenuation, this impulse would travel into medium. No, it doesn't work this way. So when you measure on the surface field caused by these currents, you cannot say field is caused by currents only in such a layer. No, with time current is spread. There are parts of the medium which give main contribution. There are parts weaker, but you cannot say exactly what is the range where currents are greatly dominant. So it's now, so that's one comment. Now, just a second. Now let us, so that's diffusion. Now let us consider a little more complicated case. Suppose instead of impulse, instead of step function, we have impulse. What would happen in this case? Can you help me to resolve this problem? What I'm trying to do now, I would like to explain. I will try to explain you what happens in the case of sinusoidal oscillation. That's time domain. Now we have to understand what does diffusion mean in the case of sinusoidal effect. Sinusoidal oscillation. Suppose instead of step function we have impulse. Can you help me to find diffusion picture when transmitter creates impulse of current? That's simple. So suppose we have that's current, that's time, that's width of the impulse. How to solve using previous result, how to find answer. Correct. Very good. So each impulse can be presented as two step functions which are equal by magnitude, but they have different beginning, and minus A, that's our T. If you add both of them, you will get impulse. It's not very good approach. I do believe it's a very good approach to treat impulses as two-step functions. Therefore, that's our input. So what happens if transmitter is the pulse? At the moment t equals 0, surface currents arise where? On the soil, on the surface. And then they start to diffuse. True? Do we know expression? No, we know. Current, Kx, at moment t equal constant, unit divide T3 T minus A over T. Let us take this interval of time. What happens during this time interval? Help me please. But now I need your help. Do we have influence of second step function during this time interval? No, because it didn't come yet. It didn't arise. So we have what we already discussed. What we consider, we know current starts to diffuse. Very good. Now let us look at this expression more carefully. A equal gamma mu z squared over t. What is the dimension? 4. What is the dimension of this quantity? Meters? No. The same as can you take exponent in power 2 apples? As time. There is no way, no way. Always argument of function must be dimensions. You cannot divide apples to potatoes. You cannot take product of them. You cannot. Always argument must have 0 dimension, no dimension. So therefore you don't need to think about this whole product. You have to look time here. Therefore A must. Now, so it's a time. It's some kind of time constant for each point. Now I would like to ask you a question. Tell me, please. If conductivity is high, they're relatively high. Tell me, please, currents on the surface stay longer or not? Longer, no doubt. Correct? Let us remember. Now, depending on conductivity of the medium, our current starts to diffuse. If it's very high conductivity, they practically will stay on the surface. Let us pay attention to this case. Something is not clear? I don't know why it's sorry. Thank you very much. It was 1/2, so it must be safe. Now, so current starts to diffuse. Then what would happen? New step function arises. How currents will travel due to this function? Exactly at this moment t equal tau, again surface currents arise on the soil, correct? But now they will travel in opposite direction. Then they start to diffuse. So, yes, sir?
What are those currents trying to retain? They're trying to keep the magnetic field and this at that instant?
Surface currents are trying to keep constant magnetic field, which was before. So, for instance, if we have this step function, let us say this step function of clear. What was the magnetic field before? 0. Therefore, surface currents arise in such way that they cancel primary magnetic field. And it will remain 0. The same happens here. Did I answer the question? Mm-hmm. Now, how to calculate total result after impulse? Add them together, or more precisely, subtract. Correct? So, we can write that expression describes diffusion when time less than width of the impulse. When we are measuring later, what would be our result? Jx, function of z and time. Sorry, I have to correct. Jx, z time equals the same constant. Here unit T1 half E minus T over tau. What happens here? Unit. Do you follow me? What is it? It's effect due to first step function. That's effect due to second step function. But what I have to write in the denominator? T plus or minus? Minus. Oh, that's much better. T minus T half, because that's the start. E minus, oh, I'm sorry, tau over T. E minus tau A. Minus A. T minus. That's all. So let us pay attention one. I'm sorry, I made it. Let us assume A is very large. I wanted to call it time constant because it's time, A is almost time constant. Now, let us ask ourselves, suppose A is very large, high conductivity, very high conductivity. So what happens after this step function? Current remains on surface. Then if A is very large, A has dimension of time greater than T capital. Then current still will remain on the surface. The next step function arises. So what would happen? Current starts opposite. So some of them will be 0, 0. Now, the same is true if you start to consider very large distances. So you will have compensation effect. So when we have sinusoid with high frequency, in effect we have what? You can tell me it's not sinusoid. And I don't pretend it's sinusoid, but it looks like sinusoid, correct? Well, there is small differences. But it's a system of pulses, which go in one direction, another direction, one direction, another direction. So if it's a time interval is very small, you don't give time for currents to go into. It remains on the surface. So it's not skin effect, it's a compensating effect. So what we observe at early stage, we do observe in high frequency domain. In effect, time domain is simpler than frequency, because it's a pure diffusion phenomenon. You make step function excitation, the currents go down slowly or quickly depending on resistivity. In the case of sinusoid, you have two phenomena: diffusion and superposition of all impulses, or compensating effect. But again, what you do observe at high frequency, you do observe in the early stage. Now I would like to clarify one more question before we will go to practical cases. Have time? We have. Back to simple case of step function excitation, which is important for us, no doubts. Now, but yes, so that step function, ideal step function. Now let me take RAM time, what is really takes place. let me ask you a question. What do you think? You measure at this moment, not inside, outside. Suppose it's a good conductor, very good conductor. What would be difference between field which we measure when you have step function or ramp time? Huh? Currents, since it's a good conductor, currents remain on the surface. That's all. Now one comment and then second comment. That's not serious comment, but useful because many strange things arose around very simple phenomenon diffusion. Now, let us take tank with water. Here, high concentration of iron. High. Here, low. What happens with ions? They start to diffuse. So if we are in iron, let us call this iron. He was here at the beginning. I promise you, time with time, it will be somewhere here. Correct? It changed position. No doubt. And its motion, on average many ions, is described by heat equation. Now let us consider our story. Current has component only in this case, which component? X. So therefore let us take iron for this model. And then we will consider later for our due to loop later. Let us take this iron. Time goes on. What happens with this iron? Can this iron be in the depth, suppose that's depth 1 meter? Can we find this iron on the depth 50 meters? You remember our lovely graph? Current density over current on the surface. You remember? That's diffusion. So I would like to discuss with you both pictures together. So in this model, current density has component Jx. As velocity of car has velocity Vx. Can car be in another place except this line? No. Always it will remain in the same level. What is it in this case? How to combine these two graphs? First of all, problem is clear. What this picture tells, all ions which are located at this plane, they forever remain in this plane. All currents which are located in another plane forever remains in this plane. What this graph tells? That's time velocity. Correct? Time gamma mu. I don't know why it's shown in this way. Doesn't matter. Let us do as it was before. T gamma mu That's Jx over J naught x. Z1, Z2, Z3. How to combine these two graphs?
This relates to the magnitude of the current.
Exactly, nothing else. This graph tells you on the plane Z equals Z1, 100 meters beneath Earth's surface, density of current or amount of ions per unit time per unit area with time changes in this way. So let us call ions depth Z1. On the depth Z2, what is it? Ions, different ions. They are a great distance from each other. So ions, how this graph shows how their density changes with time, how many are moving through unit area. So, understandable, that happens in all our time domain methods with loop and loop. So please don't think that there is complete similarity between Mohs diffusion of ions due to different concentration and behavior of the current. Unfortunately, many years ago, somebody used old known results of diffusion and introduced such strange concept, smoking rings. When you smoke, you have ring near mouth, then with time this ring appears in greater distances. So I didn't meet one person who would not be poisoned by this superficially pleasant picture. He sincerely believes, yes, in time domain there are some smoking rings. It's simply smoking effect, not smoking ring. Yes?
Is there, rather than talking about the actual current supply, is there a way that light is changing inside the body? Is a sort of smoking analysis?
No, not at all.
We're having different different current strengths arising at sort of different depths as a function of the way that the flux is changing through a given depth rise, if you like.
Just a moment. Let us slowly. When we say, first of all, it's not very good in any profession to introduce slang. Smoking ring is a slang. We are a very respectable profession. We have classical names for each phenomenon: diffusion, skin effect, resistance, inductance. So it's dangerous to introduce new concepts. It's only privileged great people. But when they're not great people, usually slang happens. So now let us, it's not about, I'm talking about, since we started to discuss diffusion, I decided to speak and explain smoking ring. Why smoking ring concept was introduced? In order to simplify your and my understanding. My and your, all of us engineers' understanding. That was sincere attempt behind of this matter. Question arises, does it explain or it creates confusion? For example, for me it's confusion because I do clearly see smoking. I do know what does smoking mean. At first moment, step function, correct? At the first moment, current near mouth, the same smoke, the same particles of nicotine and everything for a while they're here. Moreover, here and here, here and here, here and here. So, as a reasonably normal human being, I believe the main concept of this analogy is to show that my ions, my charges, my current, which was here for a while, will be there. If it's not the case, so therefore smoking describes something else, simply smoking. Now, what in reality we have? Let us call it smoking line. Current is smoking line. With time, does it show up deeper? No. It always remains on this depth. That's what I wanted to say. So, if this smoking ring, if our ions or electrons don't travel, we don't need this model. We need only to use classical, known for 100 years, this picture, which tells you at each depth amount of ions with time changes in this way. What is this way? Always. At any depth, at first moment except surface, 0. Then current density increases, then goes down. That's only what wanted I tell, because I don't know exception during 15 years or 16 years. Each time when everybody wants to say smoking ring, he thinks, or she thinks, it helps to understand, it helps to be confused. Because
But with fusion, if they start to have friction with the surrounding material,
Yes.
they're going to stay in the same plane.
in the same plane, exactly, except the same plane remains the same plane. So, but diffusion equation, the graphs derived from diffusion equation only tells how density of this ion changes, being in the same depth. It's true for horizontal layer mu. It's always true if you don't have charges. You have charges, it's very complicated. We will discuss it. Duncan McNeil tried to explain you. So, but that's classical picture. Understand? Understand? So, it's very good to have analogy. Analogy is a very good tool to understand many, many effects. But analogy should be proper. At least this analogy forces you, me, the other to think about something what does not take place. That's bad. Yes.
Are they confined to the x direction, or are they just confined to the plane?
For instance, in this case, x direction, when we have real transmitter loop, all currents trains the same plane, but only they are going along circles. That's the stuff. It depends what we like. Well, let us stop here. Aware about physical foundation of the matter. Let me show you completely different example. Borehole geophysics, induction logging, transmitter, receiver, layer, invasion zone. Who knows what does invasion zone mean? Huh? Good. One. No, I am sure more. More, huh? No? I see. Very often, pressure of the mud, we are talking about oil industry, about deep wells. Very often, pressure of the mud is greater than pressure of formation, and mud penetrates into formation. And instead, before drilling, layer formation had resistivity rho. But due to penetration of the mud, resistivity changes. And this penetration sometimes very large. If radius of borehole around usually 0.1 meters, invasion zone sometimes reaches 2 meters, 1 meter, and logging tools must look beyond invasion zone, because goal is to get information about resistivity of formation and using this data to get information about collector properties of the rocks. More or less clear? So, frequency of induction tool around 20 kilohertz, not 100 hertz, 20 kilohertz. Let us look what is the skin depth in this case. Of course, we can use this data, but let us do it separately. Data equal 10.3/6. Let us take 10 ohmmeters, 10 rho, and 20 kilohertz to 10.4. What would be the skin depth? (10.4), correct? Divide by 6, 1/4, 10.2. Did I make mistake or no? 10.4. So what we have? 10.2 divided by 8, 10 meters. Is it okay? Huh? But nobody worries about so relatively small skin depth. Why? Because we are talking about measuring field caused by currents in invasion zone, information. If it's around 1 meter, it means skin depth is greater than this distance. So around transmitter, mainly induced currents arise, which are defined by, again, primary electrical field. So that we will continue tomorrow.